so today I'm going to talk about this brain network. Okay, so the first thing we are going to talk is this. We know this brain is very. Can we? Okay, the brain is a very complicated thing, right? So there are all kinds of brain disease. If you are old, then you worry about the Alzheimer's disease. If you are young, then you really worry about whether you are too active, right? And if you are in between, then you worry about whether you have this bipolar or depression, right? So there are all kinds of brain disease, right? So, but luckily we also have very good advanced imaging technology like fMRI. You can take this 3D image on your brain, right? So the question is that, can we diagnose this kind of brain disease accurately and early on? So one way to look at the brain is to look at it as a network. I think we talked about network many times today, right? So the image is harder to manage, right? So if we can manage into a network, I think it's a good thing. So in this fMRI image, right? So every brain region, right? We can get time series on the brain activity or actually the blood levels, right? So two different regions. If the brain activity, they are highly correlated, then you can think that maybe there is a connection. So this is called a functional connection because they're active at the same time. Okay, but this kind of graph is kind of complicated in the sense that it is actually is not a certain graph. This is a probabilistic network because whether there's an edge or not, right, is a probabilistic estimate because we are looking at the relation between the two time series. Okay, so if we want to mine this graph, right, it's a little bit more complicated than mining this certain graph. So the basic idea is that given this uncertain graph, right, so we have a lot of brain image, right? So from this group of image, right, we want to be able to find what we call the discriminative subgraph feature, right? Because we want to find some subgraph feature which can discriminate against the positive labeled graph and the negative labeled graph. So discriminative in the sense that if certain structure only appear in the positive graph, not in the negative labeled graph, then that is a good feature. Just like, for example, in text mining, if you want to distinguish, for example, two types of different news, then you're trying to find the words which only appeared in one type of news. So then we can build a feature vector. Okay. So, but what does that mean that a feature, a discriminated feature appear in an uncertain graph, right? So, for example, now we have this 4 different uncertain graphs, right? So how about this feature BCs, right? If you look at BCs, right, BC appear in both a positive and negative labeled graph. So it is a frequent subgraph, right? But it's not a discriminative subgraph. How about ACs, right? AC appeared in these 2 positively labeled graphs, not in the negative labeled graph, right? But still, this probability is very low. So it's only discriminated if we ignore the probabilities, right? So if you view this as a certain graph, then that certainly is a discriminated subgraph. But if you look at ABCs, right? Although ABC appear in both the positive and negative, right? But in the negative, there's a very low probability, right? Because you multiply these 2 probability together, right? So that is very low. I mean, this is much higher. So this is indeed a discriminated subgraph in this 4 uncertain subgraph. Okay, so you get a basic idea. So that is what we want to mine. Okay, so traditionally in certain subgraph, that if you have a subgraph features, right, we can determine that what is the give a score to that subgraph feature by how many positive subgraph or how many positive labeled graph containing this subgraph and how many negative labeled graph containing subgraph. Then there are different utility score. No? So you plug those numbers in, you can get a certain value. Okay, But in this uncertain subgraph, then because everything is probability, so the number of positive labeled graph containing this is a probability distribution. So in a sense that this utility function also become a probability distribution, okay? And that certainly is less desirable because we only want one single number, right? Given a distribution is very hard to handle. So basically, we can use, if we find a distribution, then we can either use a mean or phi probability or mode or a median. These are all possibility to reduce a probability distribution into a single number. Because with a single number, then we can rank which subgraph is more desirable based on the score. Okay, so basically in here is that is showing that if we treat the uncertain subgraph compared with ignoring the probability, treating them as certain graph, that this gives you better result. This is the number of test example, right? Okay, and then if we treat use a discriminative feature compared with using frequent feature, that discriminative feature is better. And among all the different way of mapping the distribution into a single number, the phi probability seems to be better. Okay, so this is looking at the connectivity patterns, right? So if you look at, for example, this is bipolar, right? So if you're looking at the grayscale, it's not that clear, but if I'm using a threshold, you can see that if you have a bipolar disorder and a normal person, they are very different, right? So you can see that the network can be very different. So certainly, if we mine some subgraphs, right, that also will be different. Right? Some of them, the red one appear in the bipolar subject, and then the blue one that they mostly appear in the normal person. Okay, so the next thing we want to look at, how do we fuse information from multiple sources? Okay, so certainly, this image, right, is not the only type of information we can get. No, there are also cognitive measures, right, and then there are also blood tests, all those different type of information we can get. So the issue is that how can we use those informations, right? So one way is that we first just ignore those information and then try to get a discriminative subgraph, right? And then we use the side view information to help to do the graph classification, right? But the better way is to do the early fusion. We use the side view information to guide the discriminative subgraph pattern discovery. Okay, then we'll get us to better feature. Okay, so now we have two types of information. One is this brain network, and then the other are those side view information. They are basically is vector type of information. Okay, so how do we fuse them together, right? So basically, we use two type of two type of observation to help us do the formulation. One is side information consistency, meaning that if the brain has a problem, right? It has this Alzheimer's disease, right? If you can see it from the image, right? The side view should also say the same thing, right? So they should be consistent, right? The other is label consistency. If two images have the same labels, right? Then their subgraph under the subgraph feature, they should also be similar. Okay, so basically in here, right? So this is for example, we take two instances, right? So if we do the feature selections, right? This is under the this projected space under our feature selections, right? They are distance, right? So we say that the distance should be small, right? If their label is consistent, okay, means they are all positive or all negative, or their side information consistent with their side information too, right? Okay, so basically, if the two, for example, they have the label are consistent, then this will be be a positive number. So if this distance is large, then they will create a penalty to this objective function. We want to basically minimize these objective functions, right? If their side information should also be consistent, right? So there's another penalty variable here, okay? So by doing this optimization, then we'll be able to do a better prediction, because you can see that if we're using all side view, that's what we got. This is we only use one of the side view with the image, right? So you can see that improvement is more limited. If we consider all the side view together, that will give you better performance, whether it's accuracy, precision, or recall, or F1. Okay? So another approach is that we use this deep learning, right? So, but for all those brain image clinical trials, right? There's a problem that usually we do not get that many images, right? Because for clinical trial, usually you only get 100 images. So if we want to use this deep learning, we don't have enough data, right? So basically, what we want to do is that we want to use this multiple side view, to help us to reduce the learning instance we needed. Okay, so basically we use this network representation. We feed it in, right? We want to use a neural network to learn some latent feature, but then we use this the side view, right? So if the side view they are all very very similar, right? Then it will force the latent representation to also become similar. Okay, this is for two different instances, right? So if we do that, then we'll get some better result. So as we can see that, okay, this is by consider the multi-view information compared with just do an autoencoder. So you can see that there are substantial improvement, right? Okay. Okay. So this is basically feeding into a neural network. So you can see that, okay, if you look at the first hidden layers, right? So you can see that those are the representation which differentiate between this abnormal HIV infection with the normal pattern, right? Okay. So basically, in this talk, we're talking about now we want to look at a network representation, and then we try to explore multiple side view to see that we can benefit not only the classification test, but also because it's a network representation, right? So also give you some clinical interpretation, because you can see that certain brain regions, right? Because every brain region have a specific meanings, right? So you can see whether they are connected or disconnected, so you can interpret them. Okay, so they will see at the end of my talk. Thank you.